Thank you, Amanda. So good morning, everyone, and welcome to this Carbon Trust webinar on voltage management. My name is Graham Hunter, and I work in the business services team here at the Carbon Trust. So one of my main roles within business services is as a member of the technical delivery team. So I tend to carry out a lot of energy audits and also provide some procurement support to clients who may be looking to implement either energy efficiency projects or maybe renewable energy projects. So the slides that we are going to run through this morning shouldn't take the whole hour that we've allocated. So hopefully that will leave us a bit of time for questions at the end. So if you do have any questions as we're running through things, just please feel free to type these in as we go. And as I say, we'll do our best to see if we can answer some of these at the end. If we do run out of time, then we will respond to all questions via email as well. So please do feel free to ask any questions as they come up. So here's the agenda for today's session. We'll start with a brief introduction. We'll then introduce the basic concept of voltage management. Next, we'll provide some guidance on understanding the electrical loads at a site or part of a site. We'll then introduce the different voltage management techniques that may be considered at a site. We'll then explain how to evaluate the potential of voltage management and how to calculate the energy savings that could potentially be achieved. Finally, we will have a look at some of the more practical considerations when implementing or considering voltage management. And finally, we will run through some of the services that are available from the Carbon Trust through the Green Business Fund. So first of all, just as a very quick introduction for anyone who is less familiar with the Carbon Trust. So we are a not-for-profit organisation. We were set up back in 2001 with a mission to accelerate the move to a sustainable low-carbon economy. We are independent experts on carbon reduction and resource efficiency, and we reinvest any surpluses from group commercial activities back into that mission described above. There are essentially three elements to the work that we do. So we provide advice to businesses, governments, and public sector clients on the opportunities that are available to them in terms of trying to decarbonize or to reduce energy use within their business. We also measure and certify the environmental footprint of organizations, products, and services. And we also help to develop and deploy low carbon technologies and solutions. So the Green Business Fund, which this webinar is being brought to you through today, would fall under the advice element of what we do here at the Carbon Trust. So let's start first of all just by introducing what we mean when we use the term voltage management. So what is voltage management? Well, it is an umbrella term for a range of different technologies. So the main ones we've listed on the slide here. But simply put, voltage management reduces the voltage of the electricity supplied to equipment that you have on site, which minimizes the consumption of that equipment whilst making sure that it still remains within the operating conditions that have been specified by the equipment manufacturer. So what that means potentially is that if your site is being supplied with electricity at a higher voltage level than you actually need it to be, then you could actually be wasting energy and money, and you could potentially be responsible for greater emissions than are actually necessary. So with that in mind, one of the first questions that we tend to get asked is why might the supply voltage actually be higher than necessary? So there are a couple of steps that I'll just run through just now to explain this. So until 1995, the statutory supply specification in the UK was 240 volts at single phase with a tolerance of plus or minus 6%. So essentially meaning that the phase voltage would be somewhere between 226 and 254 volts. At the same time, the vast majority of the electrical distribution network in the UK has been in place for many, many years now, and there are quite a few sites across the UK where the phase voltage is actually normally in excess of that 240 volts. At the same time, historically, the supply voltage in mainland Europe has been 220 volts at single phase with the same typical tolerance of plus or minus 6%. And steps to harmonise the voltage levels between UK and mainland Europe were taken back in 1995 when the statutory supply specification in UK was reduced from 240 to 230 volts with a tolerance of plus 10%, minus 6%. And that remains the current UK position to this day. To simplify the market for electrical equipment further, the European Union introduced what's called the Low Voltage Directive back in 2016, and this was designed to regulate the normal operating voltage of all equipment, all electrical equipment to be supplied in Europe. So equipment that meets that standard bears a common mark and is designed to operate within a nominal supply of 230 volts. Also, the Electricity Quality and Supply Regulations, the EQS, they harmonise supply voltages across Europe at 230 volts with a tolerance of plus or minus 10%. With a phase voltage of between 207 and 253 volts. So what this means is that any piece of equipment with the EC mark can safely be operated on the local electricity supply anywhere in Europe. So what all that means essentially is that in the UK, where, as we've mentioned, supply voltages have historically been higher, equipment that is actually made for European markets is often used at a higher voltage than it has been optimized for. So as a result of that, the equipment may actually be consuming more energy than it necessarily needs to. And the diagram on the right-hand side of this slide just gives some past and present voltage levels in the UK and the EU for a bit of a comparison. So how does voltage management work? Well, the theory of energy saving by voltage management essentially relies on a fairly simple formula. So that's the one we can see on the slide here, which provides a relationship between the electrical power consumption and the voltage at a constant resistance. So the power demand can be expressed as a function of the supply voltage, which gives us that formula, power being equal to voltage squared over resistance. So that means for a simple linear resistive load, the power consumed is proportional to the square of the electricity supply voltage. Therefore, the higher the supply voltage, the higher the energy consumption. And equipment that you'll find displaying this characteristic would generally be described as voltage dependent equipment. So with a simple linear resistive load, what we're saying here essentially is that a 1% increase in the supply voltage will cause a 2% increase in the power demand. However, there are actually many different types of electrical load, and most of these are not actually simple linear resistive. So to give examples, so modern electronic control equipment like that used in ICT, so say for example a power supply for a laptop, or high frequency lighting such as T5 fluorescent tubes. So these are actually equipment that is designed to give a fixed output voltage irrespective of what the supply voltage is. And these would be considered to be voltage independent equipment. At the same time, you also have other types of loads. So to give another example, an electric motor is what we would describe as a partially voltage dependent load. So for a fixed speed motor, the power demanded by the load on the output shaft is often actually independent of the supply voltage. But you will get some of the losses that result from the motor operating inefficiently are actually voltage dependent. So here, the change in power demand for a 1% change in the supply voltage will theoretically be somewhere between 0 and 2%, but the exact proportion of that will just depend on so various different factors, for example, motor construction, or the actual operating hours of the motor, and indeed how it's being controlled as well. So with that in mind, what we'll do now is just have a look at how to actually get a better understanding of the load that you may have at any given site. So first of all, we need to understand how much of the electrical equipment at the site is voltage dependent and what proportion of the energy costs this actually represents before we can start to look at calculating the potential savings from voltage management. If a high proportion of the energy at the site is consumed by equipment where the power demand is at least to some degree voltage dependent, then voltage management will reduce the energy consumption at the site. And we've just given a brief explanation there on the screen as well. So just to clarify, so voltage dependent equipment is that where the power consumption varies with the voltage being supplied to it, so it complies with that equation that we looked at earlier, whereas voltage resistant equipment is where the power demand within its designed operating range is effectively independent of the supply voltage. It can be difficult to determine without close inspection what equipment on site is voltage dependent, what is voltage resistant, and what is somewhere in between. So we've got a couple of examples that I'll run through on the next couple of slides, just to give a bit of higher level guidance here. So the first example we look at here is just an ordinary 40 watt tungsten filament lamp. So that is a voltage dependent load, which means that if the lamp is supplied at 230 volts, which it is designed to operate at, then it will draw 40 watts of power. So for over an 8-hour period, it will consume 0.32 kilowatt hours of electricity. The same lamp supplied at 242 volts will draw just over 44 watts of power. So in the same 8-hour period, it will consume 0.35 kilowatt hours. So looking at that, obviously the difference between 0.32 and 0.35 kilowatt hours is very small. However, if we consider that that is actually a 10% difference, then you start to see, if you were to multiply, for example, a 10% saving across the site, then we start to look at fairly significant differences in terms of energy use and energy cost. Couple more examples here. So one I mentioned briefly earlier is a power supply unit for a laptop. So these are designed to give a fixed voltage output regardless of the supply voltage, which allows them to be used internationally. So a typical unit gives a fixed output of 20 volts with a nominal input voltage of anywhere between 100 and 240 volts. So the power supply to the computer is fixed, irrespective of what the supply voltage to the power supply unit is. So the total energy demand of the computer and power supply will not change, even if the supply voltage changes. So an ICT power supply unit would be deemed as voltage independent. Final example that we give here is of a typical electric kettle. This is often quite a good example to give actually when explaining voltage management techniques. So a traditional electric kettle with a resistive element is just a simple resistive load. Like a tungsten light bulb, it will consume more power if the supply voltage is higher than the nominal supply voltage. However, the difference here is that bringing water to a boiling point will always take the same amount of energy, no matter what the supply voltage. So what will happen is, if your supply voltage is higher, then the kettle will simply take less time to reach boiling point, and vice versa. If you did install voltage management and drop the supply voltage down, the only effect on the kettle you would see would actually just be that it takes slightly longer to bring the water to the boiling point. So this is where control comes in. So the fact that the kettle is thermostatically controlled means that it is in practice voltage independent. So as I say, those are just a couple of examples, but the main point to stress here is that essentially most devices that you would come across on site are fairly complex, and their power demand and therefore energy use will have multiple components which affect it. So to go into a little bit more detail here, we've got a few slides on just exactly what types of equipment are voltage dependent. So we've just selected some sort of commonly found equipment that you would tend to have on site, and we'll run through these. So we've already looked at incandescent lamps. So incandescent lamps are voltage dependent. So the energy that they consume will vary depending on the supply voltage. Just one thing to highlight here with applying voltage management to voltage dependent lighting is that the lower the voltage and power, then the lower the light output you will actually get. So you will effectively see some reduction in the light output if you apply voltage management techniques to voltage-dependent lighting. That's not necessarily an issue. We would just suggest that when considering voltage management, you also just make sure that the reduction in the light output won't mean that light levels on site would drop below the guideline levels. Fluorescent lamps are a slightly more complicated one. So traditional T8 or T12s, so the thicker fluorescent tubes that you find, these have inductive ballasts, which are also known as switch start. So these simple magnetic ballasts provide an unregulated supply to the lamp. So these are essentially voltage dependent. And again, we would just stress obviously checking that any reduction in light output does not negatively affect the operating conditions of the site. More modern, so slimmer T5 type fluorescent lamps are different. So these tend to have electronic ballasts. So essentially the voltage that is provided to them is electronically controlled and at a higher supply frequency as well. So this leads to improved efficiency in the production of light, but does also mean that they are voltage independent. Finally, on lighting, just to highlight that LEDs are voltage independent, so there will be no benefit with LED lighting to applying voltage management. They all have the same power demand regardless of the supply voltage, so the energy consumed will not vary with that supply voltage. To move on to slightly more involved technology, so again, something that we find on a lot of sites would be uncontrolled motor loads. So where modern motors are actually induction motors and tend to be large, sort of greater than 20 kilowatt motors with lower losses, these are actually fairly efficient. So when operating within 70 to 90% of their top rated output, they can be as high as 95% efficient and effectively voltage independent. So that's modern motors. However, most motors that we actually see in use are of a smaller rating and have higher losses, which make them less efficient. Also, many motors that we tend to come across on sites are often oversized for their application, which means that they are actually often operating for at least some of the time at a partial load, which leads to increased losses and reduces inefficiency. And it's these losses which lead to a larger proportion of the motor's power demand being voltage dependent. So if motor loads do form a significant part of your total site load, then we would suggest a fairly detailed technical evaluation of these motors to see if there is any savings potential, both in looking at adjusting or upgrading the existing motors, or potentially in applying voltage management techniques to these. Should also just point out that motor loads controlled by variable speed drives are not voltage dependent. So you don't have most of the inefficiencies there that we just described above. So there would be no additional savings possible through the reduction of the supply voltage here. Another thing to look at would be process loads, which can be voltage dependent. They are generally electronically controlled, and this is normally to ensure that the processes operate correctly. So most of the energy consumed in process plant will tend to be for motors and heating. And so the potential for energy saving through voltage management here is there. It's essentially dependent on how loads are actually being controlled. So again, we would suggest seeking some specialist advice just to assess the likely benefits of applying voltage management to any process loads. Electric heating is probably not voltage dependent just because it's a resistive load. So higher supply voltage will result in an increase in power demand, but like the electric kettle example that we gave earlier, that the method of control here is critical to whether the energy consumption increases with the higher voltage. So where temperature controllers like thermostats are installed and are set up correctly, the energy consumption shouldn't change with an increased supply voltage. What will happen here is that probably the instantaneous power demand will be higher, so the heaters will actually just warm up a little bit quicker. And finally, on specific technologies, we've mentioned earlier that most IT equipment is not voltage dependent. So the example we gave earlier was of the laptop power supply, but just to add, mobile phone chargers and office equipment are all generally designed to accept a wide range of input voltages whilst operating at a fixed DC voltage. So the majority of these, as I say, are regulated, so they won't consume any more energy when the supply voltage is higher. So now we will have a look at some of the most common voltage management techniques. And there are essentially three options when it comes to looking at voltage management. So the first one being to install voltage management equipment. This could be site-wide or it could be just installed to either a specific technology or a specific process that you have on site. Second option would be to adjust or modify the incoming electrical supply infrastructure. This tends to only apply to sites supplied at a higher voltage, so where you have high voltage transformers essentially. And the third option would actually just be to replace any voltage dependent loads that you have identified on site already. So to go into these three options in a little bit more detail, with voltage management equipment, there are essentially two types. So you have fixed ratio, where you are just applying a fixed reduction to the supply voltage at all times. And the other option is that you have variable ratio, where you are basically just saying that you want a constant voltage regardless of what the electrical load is. Whichever one of these options you choose will depend on a number of factors, some of which we've already discussed. A technical and financial appraisal of all the options should always be carried out before making any investment in voltage management. And final question that we would suggest asking here would actually be, does it make sense to apply voltage management across the whole site? So there are products currently available on the market, for example, where you can just manage the voltage for specific loads. So these can be installed downstream of the main electrical incomer, and can be a useful alternative to the site-wide approach if a site survey determines that specific systems, say for example lighting, can benefit from voltage management, but the rest of the loads on the site are voltage independent. Second option would be to adjust or modify the electrical supply infrastructure. So again, two ways of doing this. The first would be to install a tap changer. So this would allow you to essentially tap down the existing transformer and make a manual ratio adjustment. This would typically be within a tolerance of 5%. And the maximum reduction here would be limited by the range of both the tap changer and the current position of the transformer or transformers on site. This method is unlikely to achieve maximum savings, but is a fairly low cost option, so may be worth considering. But with each of these options, we would always advise consulting a senior authorized electrical engineer, and also your electricity company as well, to get their input into any decisions. The second option here would be to actually replace the existing transformers on site themselves. So for example, a unit offering a nominal phase voltage of the traditional 240 volts could be replaced with one offering 230 volts. And this would operate comfortably down to 207 volts. This can be worthwhile on the basis that older transformers typically have higher losses, and may also actually be providing capacity to the site that you don't need. So we would suggest just reviewing the existing transformers, having a look at their power demand and their ratings. And the final option in terms of voltage management would be to actually replace the voltage dependent loads themselves. So many voltage dependent loads are typically less efficient than voltage independent loads. So to give an example, we could go back to fluorescent lighting. So older T8, T12 lamps are less efficient than modern high frequency T5 lamps. One thing to flag here is just to be careful not to overlap any savings. So if in the example I just gave you, we're looking at installing voltage management equipment or techniques at the same time as, say, going through a program of replacing all fluorescent lighting with LEDs, it's just worth making sure that you're not overlapping any savings that could be achieved by both of those measures, bearing in mind that voltage management would have no impact on the efficiency of the LED lighting. Also, just to flag a couple of other things, so partially or variably loaded and or uncontrolled motors may be causing unnecessary energy demand at the site. So examples might be where you have a constant partial load. So maybe your motor has been oversized for the load that you actually have at site. So you could replace that with one that does actually match the load. With variable torque loads, it's probably worth investigating technology such as variable speed drives with feedback control. And with fixed torque loads, one thing that we often suggest is actually just to stop the drive when it's actually not required. So we'll now just run through the how to evaluate the potential for voltage management. So As mentioned, if a high proportion of the energy at the site is being consumed by equipment where the power demand is at least to some degree voltage dependent, then voltage management should reduce consumption. To determine this, we would always suggest that a detailed site survey would need to be carried out so that the savings could be calculated. This will involve various measurements that need to be taken on site. So would need to be carried out, at least the measurement side of things, I should say, would need to be carried out by a qualified electrical engineer. And we've highlighted the key steps of the survey on this slide. So they would be to measure the voltage and power, first of all, to measure the voltage drop across the site, to determine the proportion of energy consumption that is voltage dependent, to identify any critical loads that you have, to then calculate the potential energy savings that could be achieved, and finally to decide the power rating of any voltage management equipment that you would be looking to install. So we will now have a look at how to calculate the energy savings in a little bit more detail. So the energy savings that can be achieved on site will depend on three key things, those being the power demand and operating hours at the site, the percentage voltage reduction, and the percentage power reduction per percentage voltage reduction. So to explain that further, over the next couple of slides, what we'll do is we will just look at a fictitious case study example, which will hopefully help to explain the calculation methodology a bit further. So the site that we are looking at here is one where the majority of employees work 5 days a week, but some departments are actually operating 24 hours a day, 7 days a week. So in this case, that would be the ICT department. So in the purple box here, what we can see is that we have three main principal loads at the site. So we have mains voltage halogen lighting in the sales and communal areas with a weekday load of 20 kilowatts and zero load at the weekends, evenings and weekends. We also have older fluorescent tube lighting in the offices with a weekday load of 50 kilowatts and an evening and weekend load of 10 kilowatts. And finally, we also have the ICT equipment running with a 30 kilowatt load, and that is constant. So what we are essentially seeing there is that the maximum load on the system during weekdays would be 100 kilowatts, and the maximum load at weekends and evenings is 40 kilowatts. Just one thing to point out on that slide. So if the demand that we actually measured during a site walk around, so by taking actual measurements on site, if that was greater than what we had just calculated there as the combined maximum demand, then what we would need to do is probably just carry out another walk around and just make sure that we hadn't missed something or underestimated the loads. So for example, something we might have found in that case study example would be that the offices were lit overnight for longer than we thought they were, for example. So moving on to calculate the possible voltage reduction next. There are three key things that we need to know. So we need to know the target minimum supply voltage, we need to know the lowest normal supply voltage at the point of supply, and we need to know the maximum volt drop across the site. And from this information, we could calculate the percentage voltage reduction that could be achieved. So in the example here, just to run through, so our facilities engineer responsible for Anywhere Admin Center has decided that he would like all equipment to have a minimum supply voltage of 225 volts. The supply voltage changes with time of day, so at night it can get as high as 250 volts, whilst during the day a minimum voltage of 245 volts can be seen. The greatest voltage drop occurs on supplies to the top floor of the building, and during the normal working day this can be 5 volts less than the point of supply. So the current lowest site voltage here is 240 volts. So you're 245 minus the 5 volts, whilst the desired minimum voltage is 225 volts. So essentially here we have the potential to reduce the voltage by 15 volts or 6%. So finally, we also need to know the percentage power reduction per percentage voltage reduction. So as discussed, most sites will have a mixture of different equipment, which are either voltage dependent, voltage independent, or partially voltage dependent. And so to calculate the impact of, say, a voltage reduction, what we need to do is calculate for each time period an aggregate power reduction for each percentage reduction in the power supply. So on the slide here, what we can see is, first of all, that we have the mains halogen lights, which are voltage dependent. And so the power demand of these lights will be reduced by the 2% for each 1% of voltage reduction, going back to the formula that we looked at earlier. These lights amount to 20% of the daytime load, which will be reduced by 0.4% per 1% voltage reduction. Also, the ICT equipment, as we've mentioned, is wholly voltage independent, so this will not contribute in any way to any voltage reduction. Finally, the fluorescent, the older inductive ballast lighting, so your T8, T12 tubes. So this is so this is actually a mixture of your T8, T12, and T5 tubes. So this is partially voltage dependent, depending on which lamps we're looking at. So we said here that at least 90% of this load is voltage dependent. Therefore, we'll get the 90% times 2%, so 1.8% power reduction per 1% voltage reduction. So this load being 50% of the overall site demand and contributing a further 9% reduction in the on-site power demand as a result of the 1% reduction in the power supply. So using the information that we've run through on the three previous slides, what we can now do is actually calculate the projected energy savings from voltage management. So we can see on the slide here that the way we do this is that for each time period, we multiply the load in kilowatts by the length of the time period by the percentage voltage reduction by percentage power reduction per percentage voltage reduction. And that gives us our figures that we can see there of the 312 and 138 kilowatt hour saving. So a combined kilowatt hour saving of 450 kilowatts per week, which represents a 4.9% energy saving. If we say that this site operates for 52 weeks per year and pays 10p per kilowatt hour supplied, then this would give us an annual cost saving from voltage management of £2,340. Finally, on voltage management, just to have a brief look at some of the practical considerations when considering voltage management. So just to run through these, installation issues. So you'll need to consider, for example, how much space any new equipment will take up, where that is best to be located, as well as taking into account the need for additional cabling and controls, or just making sure that you've got a safe location for the equipment. Transformer replacement tends to be a positive, as no additional space is required for this option if it's just a direct replacement for an existing transformer. And you also get the additional benefit there of having a brand new transformer with a projected 30-year life. Annual maintenance, so does the equipment need to be regularly maintained, and if so, has this been factored into any payback calculations on voltage management? Voltage management equipment doesn't typically need a lot of maintenance, although it is sensible just to regularly check that it is set up to provide the optimum voltage, as the incoming supply voltage may change over time. Bypass switches, so do you need to install one? This might be useful if in future you need to take any systems offline for maintenance, for example. Voltage management can be an opportunity to install this type of equipment. Would you prefer to go for fixed or variable ratio equipment, as we've previously discussed? Guaranteed savings, so these are essentially assurances when installing voltage management equipment, typically, that a predicted saving will materialize against a given baseline. We would always advise, if entering into any guaranteed savings agreement, just that due diligence was carried out, just to make sure that everyone understands what the terms of this agreement are. And finally, the efficiency of voltage management equipment. So voltage management equipment does need some additional equipment to maintain operation. So it's always just worth making sure that the additional energy use of voltage management equipment is factored into any savings calculations. So that concludes the introduction to voltage management this morning. What I'll now do is just give a very brief introduction to the various services that we currently offer through the Green Business Fund scheme. So the Green Business Fund is available to small and medium-sized businesses, schools, sole traders and charities in England, Scotland and Wales. Businesses applying for support need to meet two of the three criteria that are outlined on the slide here, and also need to not have more than 25% of their business owned by an entity which does not meet the SME criteria. So we offer, as I say, various services through Green Business Fund. The first one being energy efficiency training. So this is typically delivered through 2-hour workshops, which we host across the UK. And I've just highlighted on the slide here where the upcoming workshops are due to take place and the dates when they will be delivered. We also offer opportunity assessments through the Green Business Fund. So these, depending on the size of the site and the energy spend, would either be delivered remotely or would actually be carried out as a site visit. And these assessments will typically outline the top three cost-saving recommendations for the business to improve on energy efficiency and reduce energy consumption. We also offer an implementation advice service. So this is where we can actually help businesses to find Carbon Trust accredited suppliers to install equipment. And we can also, through this service, manage a competitive tender process to make sure that customers are being presented with a number of different options, which can then be evaluated by a Carbon Trust consultant, and they can provide guidance to the customer in terms of which proposals and quotations are most appropriate to the business and offer the best value solutions. The Green Business Fund also offers a capital contribution to SMEs. So this is typically 15% of the project cost, up to a maximum of £5,000 for any energy saving projects. There is an upper and a lower limit, as illustrated on the slide there. And key things to point out. So this is typically designed for projects with a payback of under 5 years, and projects also need to be delivered by a Carbon Trust accredited supplier that can be found via the Carbon Trust website on our Green Business directory. We also recently have added a few additional services. So they are the Virtual Energy Manager service, where we can essentially remotely support clients to improve energy management processes within the business. We also offer technical webinars, such as the one that we are delivering today. Many of these are actually up on YouTube now, if you wanted to go back and to have a listen to those. And we also offer various Carbon Trust guides on specific technology areas as well. And just finally, again, something we've added to the website fairly recently is an organizational carbon footprint calculator. So this is a carbon footprint calculator for SMEs, designed to help them in calculating and potentially reporting their carbon footprint. So that's it in terms of the presentation this morning. I'd just like to say thank you all for listening.